Also, can you say again what we're solving for again, like when we're doing this? Like, what are we trying to reach at this point, like on the far left?
Oh, what are we trying to do here? All I'm doing is, okay, this is supposed to be in equilibrium. This is a force in the x direction. I'm trying to sum forces up. If I'm trying to sum forces up, I have to either take this and put it in the x prime, y prime, or take all of these guys and transform each of them, right? So I'm just doing the easier of the two by taking this guy, which is P, horizontally, and splitting it into its components. Okay, so this angle for reference is also theta, which means that this is 90 minus theta, and so this became theta. Okay? Hopefully the end result will be worth it, you will see for yourself. Alright, so I'm just going to sum forces along the x prime and the y prime directions. Along the x prime direction, and let's say that forces along the positive x prime are positive. So I'm going to have minus sigma x prime times the area A by cosine theta. And I'm going to have plus P times cosine theta is equal to 0. Okay? Sum of forces in the y prime direction, basic statics. What are my forces? Tau x prime y prime times A by cosine theta. Minus P sin theta. P sin theta is pointing in the negative y direction. Look at the second equation. This gives me the following. If I just cross multiply, I get tau x prime y prime is equal to P by A. I took this A, brought it to the denominator. Okay? So this is capital A. Then the cosine theta was in the denominator on the left hand side, goes to the numerator on the right hand side, times sin theta cos theta, and if I do the same thing for the x prime direction, I end up getting the following: sigma x prime is equal to P by A times cos square theta. What do we know about ductile materials? What I just told you, right? The failure is caused when the shear stresses are a maximum. What am I seeking? I am seeking the value of that shear stress, and I am also seeking at what plane, that is at what angle to the loading plane is this going to happen. Okay, so we know for our specimen, fails when what? When this guy reaches a maximum. Tau x prime. What's tau x prime y prime a function of? Theta, it's a function of theta. By just pure inspection, the product of sin theta and cos theta will be maximum when theta is, if I say theta is 0, then this becomes 0, because I have a sin 0. If I say theta is 90 degrees, cosine of 90 degrees is 0. That's not a maximum, that's 0. If I say theta is 45 degrees, the product of sin theta and cos theta is the largest. And you know very well that when a ductile material fails by shear, it fails at an angle of 45 degrees, and this is exactly the reason, the mathematical reason behind it. Okay? So sin theta cos theta and I want to point out one more interesting thing. When theta is 45 degrees, look at this. Tau x prime y prime maximum at that 45 degree angle is what? P divided by A. Sin theta of sin 45 is 1 by root 2. Cosine 45 is also 1 by root 2. So it's P by A. Or P by 2 times A. Isn't this weird? Why is it weird? Is because if I look at the plane of loading, what's the stress there? If I look at the plane of loading, what is the value of the stress? It is the force divided by the area. Right? The area of the plane of loading is capital A, the force applied is P, so the stress is P by A. So on the plane of loading, the stress is higher than the stress at which this material is failing. And that is extremely weird, and that is why you have all this factor of safety and all the other nonsense built into your stuff. Because things don't fail when the stresses reach the maximum value according to your calculations. They fail because there is a certain material behavior that is predicated by experiments, and experimentally you can see that the stress at which a ductile material fails in pure uniaxial loading is less than the stress on the loading plane. And I just want to make a last note of this point. Bear with me for one more minute. So on the loading plane, capital A, force applied. So sigma on the loading plane is P by A, and this is actually greater than tau x prime y prime max. And which is why materials are weird, because you don't know when to predict their failure. You have to have experiments. And using the experiments, we can design a certain amount of theory. This is highly watered down stuff. But I hope it conveys the point that when materials fail, if it's a ductile material, there is going to be a certain value of stress at which it fails. This is the maximum shear stress value, which is why we are looking at maximum in-plane shear stress. I wrote it down somewhere. Next week, on Monday, after we've forgotten all of this, we will come back and then look at a brittle material and then see why it fails due to normal stresses and what is the plane of failure. Thank you very much and have a good day.
I'm kind of happy we have a third because I didn't do well. I didn't do good on the but I guess I got to do good on the